All right, let's go ahead and get back into it. Any questions before we do? Okay, so we left in the middle of this example here. So we have this curve that I graphed for you in Desmos at the tail end of the last class, and I think it looks, I can't remember which way it opens, but I remember there being a basically a loop like this. Oh my gosh. Something to that effect, right? I actually can't remember if the loop was on the right or the left, but some kind of a closed loop there. And basically we found that this curve is not simple. So this curve crosses this point 3,0 at two different places or for two different values of t. And we found radical 3 and negative radical 3. So that's kind of resetting the stage for where we ended up last time. Let's find the equation of a tangent line let's just do one of those points. So let's do the positive one. So how do we find the equation of a tangent line? Okay, so really close. We have the derivative, right? We have dy dx. But now we have to evaluate it, not at an x value, but for a t value. So what happens when I set t equal to -3 here? I get 3 times radical 3 squared minus 3 over 2 times radical 3. So 6 over. Okay, so I think I have a slope of radical 3, right? I need that for the equation of a line. What else do I need? Or am I done? If I want to find the equation of a line, what do those generally look like? So we can shoot for y equals mx plus b. What information in this do we have? We just got m. Is that all we know, though? What else do we have? We have an x and y point. So I know that 0 and 3, or yeah, a corresponding pair of x and y values are 3 and 0. So 0 equals m, which is radical 3, times x, which is 3, plus b. So what does b equal to? -3 radical 3. So I think here's the equation of one of those tangent lines. Y equals radical 3x minus 3 radical 3. We could do something very similar to find the other one, but I at least wanted to walk you through one of those equations. But think back to how you did this in Calc 1. What's the difference between how you would find an equation of a tangent line in Calc 1 and how we just did it? Or are there differences? Other than you dealing with t instead of x directly, that's maybe the only difference, but really a lot of these things are going to be common. Questions so far? Okay, so let me get a clean slide to do the rest of this. So we already sketched the curve. Equation of one of the tangent lines. So let's handle the next one. I want to find the points on this curve where the tangents are either horizontal or vertical. What does that mean? So let's pick one to start with. What does it mean for a tangent to be horizontal? Or what does it mean for a line to be horizontal? Slope is 0. So what's the thing about this that tells us the slope? dy dx gives us the slope. What was that? 3t minus 3, 3 minus 3t. that it? Yeah. Okay, so if I want to find where this thing is horizontal, then I want to do what with this derivative? Set it equal to 0. So 3t squared minus 3 over 2t equals 0. Where do I go from there? Solve for t. And how do we start doing that? Right, so if we can multiply through by 2t. Or another thing that comes out of this is, we have a fraction. The only way that fraction is going to equal 0 is if the numerator equals 0, right? So if I got 3t squared minus 3 equals 0, that comes out to be t squared equals 1. Or t equals minus 1.
So what did you say about the numerator being 0?
So for this to equal 0, basically what EV had us do was to multiply both sides by 2t, right? But the only real effect that has is the 0 and the 2t are the 0 times 2t is still 0. So really, if you have a fraction equal 0, then really you need to look at the numerator. One caveat to point out though is you have to make sure that what you have is actually a 0 and not undefined. So we found that t equals plus and minus 1, right? Is this thing actually defined for those t values? Basically, what we want to watch out for is the 0 over 0 situation. We don't have that, right? So at these t values, we really do have 0, right? Really do have a slope of 0. So I found these t values, or we found these t values, but we really want to find is the points, which I don't think we've done yet. So how do I find the points where those tangents, those horizontal tangents are? To get y?
Yeah.
I have to get y. What about x? Yeah, so I don't have either coordinate right now. So we have to plug into x and y to get both. So when t equals 1, I get that x equals 1 squared and y equals 1 cubed minus 3 times 1. So what is that point? That is 1, -2. And then something similar for the other t value. X is still 1, right? And y equals -1 cubed minus 3 times -1. So 1 -2 and 1 +2. So that's for the horizontal tangent. Where is this going to have a vertical tangent? So we related this to the slope with the horizontal tangent. If you have a horizontal line, what does it slope? If you have a vertical line, what does it slope? It's undefined, right? It's infinitely. So basically you have something that changes in the y direction, but doesn't change in the x direction. You can't really define slope the way we define it. You can't assign a number to it. But we can still work with that. We have a derivative. We have dy dx. What is it that causes this dy dx to be infinite or undefined? When t approaches 0? Almost had me. Really, the problem is where t is 0, right? That's where I'm going to get the undefined. So for a horizontal tangent, I want the derivative dy dx to be equal to 0. For a vertical line, I want dy dx, to take the form of basically something over 0. Basically something non-zero over zero. I want it to give me that, that undefined infinite behavior. You do. Or zero for what? Not zero for t. But basically here, so our dy dx is 3t squared minus 3 over 2t, right? So what's going to make that be undefined? It would, but how do you get there? Okay, that's the middle step I wanted to make sure we actually addressed. So it's really what comes from what's going to make the denominator equal to 0. That's what's going to cause a fraction to be undefined, right? So 2t equals 0, that does yield t equals 0. Then I find the point that goes along with that. This is the origin. Okay. So I think I drew this curve wrong before then.
Yeah, it was like the other way.
So it's vertical at the origin, right? So the loop looks something like that. Okay. So the left looking fish. So I don't think yeah, nothing exists left of the y-axis in this curve. How are we doing? Any questions so far? All right, so the last bullet on here we want to handle is where's concave up and concave down? How do you answer that question? What tells you the concavity of a function? Second derivative, right? So basically what I want to find here, I have a derivative dy dx, right? But now I want to take the derivative of that. So how is that going to work? Where do I want to start this? So I got dy dx, but I want to take the derivative of this. The derivative of this derivative with respect to t. So I got a lot of symbols going on here. I want to make sure we kind of know what's actually happening here. So let's start from the beginning. Did we find dy dx? We have dy dx, right? How did we get that? Right, so we got dx dt, not on this slide, on the last one, but we got dx dt, we got dy dt. Dy dx comes from dividing them, dy dt over dx dt. So we have that. So now I want to take a derivative of that dy dx with respect to t. So I kind of have to observe the chain rule to do that. So the first thing I have to do here is take the derivative of dy dx with respect to x. So basically, the derivative of dy dx. I don't have enough space to do this. Rather than me make a new slide or try to jam all this in this little margin, let's cheat. I don't care about the first derivative, I care about the second. So a whole bunch of different ways to represent this, but let's talk about it. Right, is this showing up okay? All right, so what's being shown here? So the game is still the same. I want to take the derivative of dy dx with respect to x, right? But what really is my so what's my first, but when we're dealing with parametrics, what's my first input? It's no longer x, right? It's t. So that's why we kind of have to use chain rule. We do, in essence, have a function composition here. So the first thing I want to do is take a derivative of, so I got my first derivative. I'm going to take a derivative of that dy dx with respect to t. And then I'm going to divide that by dx and t. So that's the setup. We now do an example of that, or apply that to the example we've been working. Okay. So let's go back.
Are you finding the second derivative of each function and then?
Basically, like the chain rule working from the outside in. So the first thing we're going to do is take the derivative of dy dx with respect to t. Can I take the derivative of 3t squared minus 3 over 2t? How do we do that? Quotient rule, right? How does that work? So derivative of the numerator times the denominator intact. Over the denominator squared. So this right here is the derivative of, basically it's the derivative of dy dx with respect to t. So we've done like this, in essence, the outside, like the outside step of the chain rule. But now to really find, basically this is what we're really after. The derivative of dy dx with respect to t. That thing divided by dx dt. So can I simplify this thing at all and fit it in the space?
6t squared, 6.
Is that all it is? Okay.
Squared.
6t squared minus 6 over 4t squared. That's like the inner step of the chain rule. So basically you have dy dx is a function unto itself, but that's a function of x, which is a function of t. So basically, because we have this function composition, we have to deal with those layers one at a time. So what is dx dt in our case? 2t, something we found before. So if we bring all these things together, what do we get?
Oh, the T.
That's a visual aid for me to figure out how to divide this road reciprocal. So 6t squared minus 6 over 8t cubed. So I'm going to stop. I'm going to stop right there. We don't have enough space to say where it's concave up or concave down, but let's at least talk about how you would go about that. So that's the second derivative in this parametric curve. What about that tells you if it's concave up? If it's positive. And if it's concave down, it's negative.
You have a question about this in the test?
You may.
Were you plugging again to find this?
You don't really plug in anything, but here's what you probably did. In Calc 1, one thing we didn't talk about is, so we talked about concave up, concave down. What's in the middle? What are those places called where the concavity changes? You can find inflection points by doing what? If you set this second derivative equal to 0, basically you can find those inflection points. And then from there, like basically that kind of partitions all your t values. Then you have a better chance of finding out what the concavity is around. How we doing?
So we have, so we find the interval of concatenates?
Yeah. So we're gonna stop here, but at least on this example, but that, I did want to walk you through how to find a second derivative since it is more involved than it might seem like it would be. It's complicated to do, and especially like because the derivative comes from us dividing expressions, you're pretty much always going to have a derivative, or a dy dx, first derivative, that is something fractional.
But in the horizontal, solving for with the derivative equals 0, but then the vertical we're solving for it's defined.
Oh, sorry, say that again.
In the horizontal and vertical, have
Yeah.
to take a step back. Or we're just for horizontal, we're solving basically where the derivative equals 0 is.
Yep.
And then figuring out those values with the vertical we're solving for is undefined.
Yep.
Okay.
All right. Anything else? Did a lot with this one curve. So this curve right here is called a cycloid. Basically what it looks like is this. It's kind of like these series of arches. So what's my parameter in this example? There's no t, right? Theta this time. So yeah, that parameter doesn't have to be t. Basically, it's whatever unites the x and y curves here. So let's at least find the slope of the tangent line at that point. How do we do that? Okay, what is dx to theta?
R. R.
Yeah, so I'll leave it factored for now. Yeah, so r is a constant, so I can just kind of carry it with me. If dx d theta equals that, dy d theta equals what? R times sine theta? Yeah. So that leads me to what? Dy dx is equal to what? Sine of theta over 1 minus cosine theta. Good? How we feel about finding that derivative? The dy dx derivative. Can I use that to find what I asked for?
Treating R as a constant,
Yeah. Basically, R tells you like how large those arches are going to be. But the rate of change doesn't really depend on it. It divides out. So how can I find the slope at the point where I care about? So if I plug in pi over 3 here, I get sine of pi over 3 over 1 minus cosine pi over 3. What is sine of pi over 3? Root 3 over 2 over 1 minus a half. So all told, radical 3. Questions? All right, so I think we've done that. How would I find where this thing is horizontal? I want dy dx to equal 0. So that's in general, that is exactly what I'm looking for. And then in our specific case, that comes from sine of theta equaling 0, right? Where does sine of theta equal 0? So basically, every multiple of pi, right? While we're at it, question?
Why do we not use the whole UI?
Here's why. So let's back up. Here's why the shortcut we just took works. So if we set the whole thing equal to 0, how would we solve that? Multiply both sides by 1 minus cosine theta, right? So then that becomes sine theta equals 0 times 1 minus cosine theta. So because I'm setting this equal to 0, another thing I can put down here, if I had a over b equals 0, what can you say about a and b right there? If a over b is equal to 0. What can you say about a? A has to be 0. One more thing to point out, what does that say about b? 0. Has to be anything but 0. So that is one thing we can check for, but if I have a fraction equaling 0, that means the numerator has to be 0 and the denominator has to be non-zero.
So it always be the case.
That all it is. So because of that A and B parallel I did down there, what should we check for? I mean, we need to look at that anyway, because that is going to give us where we have vertical tangents. So where does 1 minus cosine theta equal 0?
0.
Is it really the same places?
Not the exact. It has to be.
Oh, the multiples of 2 pi. Okay. So that gives us where cosine theta equals 1, which is negative 2 pi, 0, 2 pi. And then on the horizontal side, what did we say it was? Oh, okay. Yeah, so now let's actually answer this thing. So where is this curve truly have horizontal tangents? So, okay, that's true. So one thing I want to be really sure about is, why are we now saying it's odd multiples of pi, where we just said it was every single multiple of pi?
Even multiple.
Right, so I can't tell you anything about the tangents at oh, I can't tell you about the tangents at the even multiples of pi. So what is the tangent, or what is the tangent doing at 2 pi? Vertical, right? So if I kind of peel back to this curve here, this is a 2 pi, this is a 4 pi. So these are where the vertical tangents are, right? Where did we just say the horizontal tangents are? Does it make sense they have to be in the middle of those arcs? So the first one's going to be here at 1 pi, and then they're going to be spaced out every 2 pi thereafter. So the horizontal tangents are the odd multiples of pi, and the vertical happen at the even multiple of pi. You're talking about that fork symbol?
Yeah.
This I don't know what the name of the symbol is, but that means basically what it says is T is a member of this set of things.
In our specific data, but that's.
Yeah, no, it's definitely should be consistent. Yeah, theta has to belong to something that lives inside that set. Question.
So then if they were somehow switched and it was like the cos is the one that was horizontal, like even if this was like an even function.
Yeah. So I suspect that if I swap sine and cosine in the definition of this curve, I think I still have the same arches, but I think they'd be pushed out. Like, I don't think it would start at the origin like that. How we doing? Go. So for the first part, we found the slope at a specific value of theta, right?
So is that the answer, or do you have to use that to find the tangent?
Yeah, so I modified this question to not to find the tangent, the whole tangent, but to find the slope of. Abbreviating because we did a full tangent line just a few minutes ago. How we doing? Okay. What now? Area. How do we find areas? So let me go remind you what this curve looks like again. Actually, I'm going to enlarge it and I'm only going to draw one arch. I only care about one arch, right? Think back to, actually not even Calc 1, because we did a lot of integrals here. How do you find the area under a curve in general? Integrating. You integrate something with respect to x. What's the something you integrate? A function of x, right? So typically what we do is this, you integrate from some lower bound to some upper bound function of x with respect to x, right? Is this equivalent to me writing this? At least the way we used to do this? I mean, typically when we have a function of x, that function notation is standing in for y, right? So we're essentially going to find this area the same way. I'm going to integrate y dx, which is what you've generally always done. But how's that going to look when we start thinking about parametrics? So I'm going to leave the bounds off until the very end. We got to figure out what the bounds actually are. But what is our y here? R times 1 minus cosine theta. What is dx? So I'm going to unpack this a little bit. I'm going to call this y times dx dt times dt. Do we believe that all three of those integrals that I wrote on the right-hand side are different manifestations of the same? That's essentially what we're doing here. So the first thing I wrote down is y. This next thing I'm going to write down is dx, which Caleb, I think you already said it. 1 minus cosine theta. And to be clear, where'd that come from? Right, so this right here is dx d theta, and then d theta. So this is the thing we're going to integrate. But we have to know how far to integrate it. How do you know it's 0 to 2 pi? Right, so finding those vertical tangents did in fact tell us how far apart the arches, like where one ends and a new one begins. So we can absolutely use that information again to tell us that we are integrating from 0 to 2 pi. So here's the setup of the integral. Any questions with that so far? Okay, so let's clean it up a little bit. So integrate from 0 to 2 pi of r squared times 1 minus cosine theta squared. So 1 minus 2 cosine theta plus cosine squared theta d theta. Is this an integral we can do? What's that? Absolutely. Right, so the one we can integrate directly. 2 cosine theta we can integrate directly. Cosine squared theta, we got to do a little bit of manipulation too. We've done this before, but it's been a while. Do you remember how we turn that into something we can integrate? Half angle, double angle, depending on which side you're looking at. But one angle or one identity we have is cosine 2 theta equals, so 2 cosine squared theta minus 1. And then basically I want to solve for cosine squared so I can drop this in for it. So cosine 2 theta plus 1 over 2 equals cosine squared theta. That sound familiar? I know that was a couple months ago, but I think we've done it a bunch of times. So now r squared times the integral from 0 to 2 theta of 1 minus 2 cosine theta. Actually, can I call this 3/2? No, let's just not skip any steps. Plus 1/2 cosine 2 theta plus 1/2. We okay there? Can I do the integral now? Okay with you if I combine this first? The integral of 3/2.
Theta.
3/2 theta. Negative 2 cosine theta. 2 sine theta. And 1/2 cosine 2 theta.
Sine of 2 theta.
1/4. Divide by 2. Yeah, so when you remember, just like when you take a derivative, if I was going to take the derivative of sine 2 theta, it would be the cosine of 2 theta times the derivative of 2 theta, so times 2. When we integrate, we have to divide that out. So what happens if I start plugging in stuff? Oh, all the signs go away, so I really just get 3/2 times 2 pi. The only thing that comes out non-zero is 3/2 times 2 pi, right? So 3 pi r squared. So that's the area of one of these, and it's going to vary with how big the arches actually are. How we doing? The one big takeaway I want to make sure you have here is, in general, how do we deal with integrals in parametric form or in parametric curves? Really come from these two things here, which are one is a re-expression of the other. So you're integrating y dx. How are we doing so far?
So when you say we're finding the vertical or horizontal, and whatever the word was in the previous
Yeah.
example, but the horizontal, that's like the maximum, and
Yeah.
vertical is kind of where it's continuous.
Yeah, basically, you know, at that point, so either the left or right end of this arch. My drawing isn't really reflective, but it decreases so sharply that the tangent actually is vertical, it has undefinable slope. Question?
What is R?
R is a constant, basically it's the radius of this thing. I could have dropped a number in there, but basically that R is a constant, tells you how big these things are. What else? What else have we done with calculus? I might come back to this. Now let's at least set it up. Let's do that. Let's set this up even if we don't actually like finish the full integral. So I want to find the area enclosed by the x-axis and that curve. So how should we start? How do we find the bounds here? So it's enclosed by the x-axis and the curve, right? So I'm gonna try to avoid looking at what this thing looks like, but it's one of two things gonna happen, right? It's either gonna look like this, or something like the mirror image. Basically, you're gonna have an area between the curve and between the x-axis. I don't know if it's above or below. We can find that out. That's exactly how you find. That's gonna how you're gonna pin down your balance of t. You want to know. Basically, you want to know where it crosses the x-axis. Where does it cross the x-axis? Wherever y is equal to 0. So y equals 0 gives us this equation. 2t minus t squared equals 0. Or how can we solve that? Right, so factor out of t. So now I get t equals 0 and t equals 2. So that's important. That gives me my bounds. Where can I go from? We're gonna go from there. Okay. Definitely need dx dt. What is that for us? 3t squared. Cool. What's that? All right, let's set up the integral. The integral from 0 to 2 of what? So 2t minus t squared, because that is y, times 3t squared dt, because that is dx. It's probably it, but one thing I think we should be sure of is, even though we're not going to fully compute this integral, let's make sure it'll give us a positive number. So, in other words, can we be sure that our area is actually above the x-axis or below? I don't think we know that for sure yet. Can we find that out? All right, so let's choose the one right in the middle. If t equals 1, what is y? Positive 1. So I think the values of y are positive inside the interval, so I think this integral is good to find the area as it's written. Questions? Go ahead.
What do you think the curve was under that?
Good question. If the curve was underneath the x-axis, how would we fix our integral? That's all you do. Yeah. Basically, you would find an area that would be negative, take the absolute value of it, put a negative sign out front. That's either one of those is gonna fix that issue. Anything else? Go ahead.
If we have like an area on the exam, do we need to know like the other methods we also use for just area that we can do?
No, there's one more thing. Did you your hand up?
Yes, for the bounds again, so this is just with like the y values.
Yeah.
So the one we did previously with, that was 0 to 2 pi, it wasn't from horizontal and.
No, so here's the thing. The last one, we could have done the same thing. But because we dealt with the same exact curve in the prior example, we just recycle that information. But here, let's say this is the first time we looked at this. If I want to find under one arch there, I could still set r times 1 minus cosine theta equal to 0. And I believe that would still give me 0 and 2 pi for a pair of values. Yeah, we just took that shortcut because we dealt with that example before.
I can't remember having ever seen. Yeah. That's all, I'm not gonna promise you, I just can't remember having seen. Okay.
In case that you need to find like an area down like by the y-axis, would
Yeah.
just be the opposite.
Yeah. If I wanted to find the area enclosed by the y-axis, so let's change the question. If I wanted to find the area enclosed by the y-axis in the curve, what would I do? Set x equals 0.
Then you should also use X and then.
You have to make a lot more changes to. Yeah, basically you have to. Actually, I don't even know if you would have to do that.
X, and then go Y and T.
Yeah, you could do that. All right, so arc length. How the heck do we do arc length? Do you remember how we set it up? Like, let's just set this up from scratch. So I got all basically. The motivation here is I want to take all these, so this is not linear, right? This is all smooth curves, but basically. We're gonna adapt the Riemann sum so I can, instead of looking at the area or the length along curves, I'm gonna look at the length along straight lines, right? So how do I find this length along a straight line? Doesn't it just come from like a small change in x and a small change in y? This is kind of how we set it up before, right? So there's a small change in x and a small change in y. How do I use those changes in x and y to find out the hypotenuse there? Square root of dy squared plus dx squared, right? What if hypothetically both of those things are a function of t? So if you remember the way we did this in the past, where basically you're integrating the square root of 1 plus dy dx squared. Yeah, I think it actually comes out a little more intuitive, maybe a little more symmetrical. Because now essentially the integral we're taking is to find the length. We're integrating from t equals something to t equals some upper bound of the square root of dy dt squared plus dx dt squared dt. No, that is not the second root, that's the square of the first root. It depends on what you're doing. So we only have a couple of minutes, but maybe we can at least talk about how to approach one. So I want to find the arc length along the unit circle, which you probably can figure out in your head. But how would we set this up? So the question that was just asked was, how do we figure out the bounds? This one, what are the bounds? They're kind of given to you, right? If they weren't given to you, could I still figure out what the bounds were? If I want to set up an integral to get the arc length along that circle, I only want to go around the circle one time, right? Which means I want my difference in t to be how far? 2 pi. Oh, 2 pi. Yeah, 2 pi r, but the radius in this case is going to be what? It's 1. So yeah, by default, unit circle. So that's how we get the bounds. I'm not going to try to shoehorn the rest of this into the last minute we have. So I said I wanted most of Monday to be review, right? And it will be. So I got a couple of arc length things to walk you through. And then that'll be it. So we'll finish this up in the first several minutes of Monday, and then we'll basically whatever questions you have for me, bring those and we'll talk about them. And then I think I posted an announcement on Canvas, but I'm changing my office hours next week, so on Monday, I have office hours from 11:30 to 1:30. And Wednesday, normal time, no Friday.
Will that be going forward?
Nah, it's just next week.